So I normally start with thermistors and run through those, and then we talk about potentiometers, pressure sensors in that order. I'm trying to think maybe doing something a little bit different and just really showing you the difference between the thermistors, potentiometers, and pressure sensors first, as far as electrical design and how they work and voltage readings, and then we'll jump into the core of the thermistor section. Okay? So to do that, I just want to draw a simple circuit for you. This is the inside of the engine computer. And I'll draw our thermistor circuit first. And then I'll draw our potentiometer circuit. I want to really show you the difference in these. Five volt, 5 volt. All right, so this one, this is our potentiometer or our pressure sensors. And this one would be our thermistors. What is going on with my smartphone? Freaking out on me. I don't know why. All right, first thing would be, let's talk about how they're measured. And this shouldn't be new. Some of this is a repeat really from section 2. If you can think about our pull-down switch input designs, I was drawing pictures like this, where I was drawing a computer, a positive source, a resistor, and a switch. And then we talked about this voltage sensing circuit here. You guys remember that discussion? And I said that this voltage sensing circuit that we're looking at, it doesn't support any type of current flow. Our current flow through this circuit would be in this direction. All we're doing with this is monitoring the circuit. And I believe I told you guys that we can compare this leg as our positive voltmeter lead and this leg as our negative, and we're just monitoring, we're just watching the voltage level right there on that circuit. Does this ring a bell? No? Yes? Silence is not good.
Silence is gold.
I did talk about this. This is a pull-down circuit design. If the switch is open, what is the voltage here? Whatever the source is. Okay? If my source is 5 volts, what is my voltage here? 5 volts, very good. No voltage drop is going to occur here as long as the switch is open. This will remain at 5 volts. Very good. Well, when the switch closes, this side here will drop to 0 volts right there. Are we good down here at the bottom? We sure? So this isn't new. What's the voltage sensing circuit do? It monitors the circuit. Does it really look like that? No. Do we care what it looks like? No. Right? Visualize it. Doesn't matter. Up here. What is this? It's another one. I'll put a V in there now, and I'll put a V in there now. We'll make this our positive and our negative, our positive and our negative. Does that voltage sensing circuit support current flow? No, it does not. Talk on current flow for a second. How much current is on these circuits? What did we say earlier this morning when we reviewed the heater circuit of that O2? How much current is on a sensor circuit? Why are sensor ground voltage numbers so low? Why do we only allow 100 millivolts when we measure a sensor ground?
200 to 800. I forget.
No.
I'm sorry. That reminded me of like asking someone a two-part question, being like, is it A or B, and your answer is yes. Sorry, Dave. That was way off.
I have no idea.
I'm asking amperage. What is the amperage of a sensor circuit? Is it high? Is it low? Think about it. We have an engine computer that's measuring voltage levels. Do we need the current flow to be high? Why would you pass current flow through a circuit just because you can? No. These are microamps. Okay, that's what I was getting at. I mentioned when we talked about the O2 circuit that the heater circuit was high amperage. The signal circuit, you're right, 200 to 800 signal circuit. That's the signal circuit. But how much amperage is in the signal circuit? Microamps. Like millionths of an amp is a microamp. You guys understand that it's not even measurable on a regular ammeter. It's so small, you can't even measure it. I've tried using my internal ammeter and I can't measure it. It's that small of an amperage. But is there still current flow through these circuits? There has to be to have a voltage drop. If you take this bottom switch input, this pull down design, and close it, we close this switch, is there now current flow through this circuit to ground? Yes, you have to have current flow for that voltage drop to take place across that resistor. But here's the point. It's so small that all we're really doing with this circuit, I know there's current flow, but all we're really doing is monitoring the voltage. So I know the position of the switch in the bottom picture. That's what we're doing. You come up here to the thermistor, you'll see something similar. Picture this resistor out here going to ground. What are we looking at? Just ignore this down here. What are you looking at? You're looking at a pull-down switch input. You're looking at something that would be exactly like that. Does it matter if the ground is in here or if the ground is out here as far as current flow goes? No. The answer is no. We'll talk about why the grounds are running there in a second. But what's different now? There's no switch. Okay? What do we see here? I see a resistor. And I'm missing something in my picture. There should be a line through here. When you see that on a diagram, what that's telling you is that is a variable resistor. So get used to that symbol. You see a squiggly line with a line through it. That is a variable resistor. So this thing will vary its resistance, which will vary the amount of flow. Think about that. If the resistance out here is high, the flow through the circuit will be less than if the resistance out here was low. That would allow more flow through the system. So it's changing flow rates. Again, we're not measuring current, but with this change in current comes a change in voltage. This circuit here, guys, is what the computer's monitoring. That circuit that I just drew in blue will be affected by the resistance out here and the resistance here. I've used this analogy a lot. I think it really gives you a good visual. It may not be entirely accurate. It's not accurate, but it gives you a good visual. And that would be, picture a garden hose. We can even draw it green. Picture a garden hose with two kinks in it. Okay? And we got water in here. And the nozzle's closed on the end. We'll draw it that way. So this nozzle is closed. What's the pressure here, here, and here? Is it equal? Sure it is. You got that hose all kinked up. You don't know it till you open the nozzle. It's real hard on both sides of the kink right now, right? Open this nozzle up. See if I can illustrate this. open the nozzle up, and what we'll have is we'll have a high pressure here, we'll have a lower pressure here, and we'll have a trickle here, if you can picture that. If I squeeze this one tighter, make this resistance tighter, which in my analogy would be this resistance, what does the pressure do in here? It goes up. Very good. So when this external resistor is high, what's the voltage or pressure do in this leg? Goes up. So we have high pressure here. In this one, if I open this one more, what happens to the pressure in here? It goes down. So if I drop my resistance out here, my voltage in here, in this leg of the circuit, drops. You guys follow? All right. On this side, what if I change that resistor? If I squeeze this one tighter, what happens to the pressure in here? Squeeze this one tighter. Water's flowing this way. Goes down, right? Opposite. Squeeze this one tighter, pressure goes up in here. Squeeze this one tighter, pressure goes down in here. So we have the exact opposite effect in this leg of the circuit. Point is this, do you see how this resistor and this resistor affect what we see in the signal circuit? This is your thermistor circuit. This is how they all work. Every single thermistor from the dawn of time when they started putting them on cars till 2014. Intake air temperature, and engine coolant temperature, and transmission fluid temperature, and in-car temperature, ambient temperature, you name it. Anything with the name temperature sensor, they work like this. This is how the circuits work. All right. Our pots and pressure sensors, a little bit different. What do we notice about these? The 5-volt ref, the 5-volt reference circuit, that's what it's called, or our 5-volt supply, there's no resistor there. Can you see it? That's one of the main differences. Right here, there's no resistor. The other thing is this voltage sensing circuit is not monitoring like it is on the thermistor. You see how we're monitoring the reference wire, which actually is the signal wire, but down here we have a separate signal. So to name these, this would be my 5-volt ref. Get used to that term. This is my signal, and this is my ground. There's other names for that sensor ground we'll cover as we go. Up here, this is 5-volt ref, but it is also the signal and ground. Now, let me pause for a second. I want to give you guys some perspective. We're talking about throttle position sensors, we're talking about map sensors, we're talking about engine coolant temp sensors, intake air temperature. All of your critical main inputs fall into these two categories and how they operate. Are we covering a lot of material? You know, chapter 6, 7, 8, 9, 10, and 11, we're really focused right here. 6 chapters on this. There's a lot of theory, a lot of operation, a lot of variables, but the core, the foundational part, would be within these 2 pictures I have drawn here. It's not that complicated. All right. Do you guys understand that up here on the thermistor circuit, that this signal wire here changes all the time? External temperature out here is what changes this resistor, changes its resistance, changes the signal voltage. On a potentiometer or pressure sensor, do you understand that this blue leg that I just drew is always 5 volts? It never changes. It's a completely different design. What you're looking at is the drop in voltage will occur external out here. So we have 5 at the beginning, and we have near 0. It won't be exactly 0 at the end. Our drop occurs across this resistor, and the only thing that the signal is doing is we're tapping into different sections of that resistor so we can read that drop. If this, it's known as a wiper. So if you can picture this being attached, say, to the throttle shaft, when we move the throttle, this wiper is going to move up and down. So if the wiper is attached up here, the voltage, the signal voltage to the computer will be high. And if the wiper is contacting the resistor in that location, the signal voltage to the computer will be low, and that's how it operates. This will stay at 5. Down here will be very near 0, and we'll have a drop that's occurring on the resistor that we're reading that value back to the computer. Very basic, simple circuit. Questions so far? It's not too bad, right? All right. Now let's talk about our reference. Where is this 5 volt coming from? There will be something in the computer. It's called a 5 volt regulator. What does a regulator do on an alternator? It will maintain a specific voltage. If you have an alternator, say, that's designed to maintain the system at 14 volts, and by the way, that alternator has the capability of producing 20 volts, so we're kind of throttling it back, controlling rotor field strength. When we turn headlights on, or our blower or rear window defogger, and we put a draw on the system, if we check battery voltage, it will still be at 14 volts with those loads on and with those loads off. It is doing that by regulating our rotor field strength, which regulates voltage. The point is, with changing demands, voltage stays the same. And it does that by varying current flow. So what's this regulator doing? We have a 12 volt supply from the battery. It has a constant ground, and it has an output of 5 volts. And this 5 volt output will be constant and not changing. Every single engine computer has one of these. In fact, this goes more than just engine computers. This is an industry standard with computers using a 5 volt reference circuit. Not just automotive computers will use a 5 volt ref for signals and inputs and outputs. Not so much outputs, inputs. Okay? This 5 volt reference goes everywhere. We talked about this again. I wish I would have recorded it on that Pacifica that had the shorted reference, if you can refer back to that case study that we did together. 2 of the places that this 5 volt is going to go is right here and right here. Do you understand that the source for this 5 volt reference for the potentiometer and pressure sensors, that's MAP, TPS, right, just to name a few, and for your thermistors, which would be your engine coolant intake air, to name a few, come from the same location? Do you see why I have a separate chapter called the 5 volt reference circuit that's tied into this week's subject, which is potentiometers, pressure sensors, thermistors. Chapter 9, I think, is the 5 volt reference circuit. We're really on the same topic, aren't we? Steady 5 volts. How important is it that this leg stays at 5 volts? Come on. All of this. How important is that that stays at 5 for these sensors to work? Now, what about this one? Is it okay that it's dropping over here? Yeah, that's how the circuit's designed. Would it be okay for it to drop on this one? Imagine if it dropped on this potentiometer or pressure sensor and you started off at 3 volts at the top instead of 5. Can you see that the entire range of that TPS, if it's a TPS, would be off? From idle to wide open throttle, the entire range of that sensor would be affected by low reference voltage. Questions? So I I want to elaborate on this more, but I need some feedback from you guys to see where you stand. Nobody's got a question? You need a break. Thermistor?
Yeah.
What's your question on the thermistor? No, this is different from the thermostat. Is that what you're talking?
I was trying to say thermistors.
Oh, gotcha. I got you. Okay.
Both thermistor diagrams.
I'm sorry. Bell, what?
What's the bottom one?
The bottom, this one?
Yeah.
These ones are your potentiometers and pressure sensors. These guys here, this picture, and this top one is your thermistors, all of them.
They're connected.
They're not connected. They're not connected externally. It's a good question. You can see that inside the computer, we're sharing a reference. Externally, they're not connected. There are some things. It's a good question. That's really what I wanted to talk about too. Thank you. There are some things we can share, and there are some things we cannot share. Do you guys remember having that discussion with Dave Subaru when we were messing with his heater circuit on his Subaru? We were mapping out the wiring diagram, and we said, this has to be this because this can't be shared. You remember that? You may not. It might have been information overload at that point. Do you understand that these circuits would work if we connected the grounds, shared the grounds? We could do that. We can share grounds on sensors. In fact, it's done that way. To be maybe electrically more accurate here, let's see if I can do it. I need a smaller eraser that would do it. It's not letting me. This would be more typical of what you'd see on an actual wiring diagram. Now this voltage sensing circuit still needs a ground, but that would be probably more accurate. There'd be a splice, and that thermistor up there is sharing a ground with the potentiometer pressure sensor. Grounds can be shared. Okay? Not probably more typical. This is what they do. You'll see MAP, TPS, ECT, IET, mass airflow, possibly all sharing one ground. And I have that in my diagram in section 9. Could I get this back to where I had it, if it'll let me? Could I take this circuit and see how I can do this? Could I share my reference? The way I just drew it, you can see that this thermistor here would have 5. We would have 5 volts here, and we'd have 5 volts up here. We would have a drop occurring here, but what would the computer be watching? Where's the signal for the thermistor? It's watching right here. There's nothing attached to it. We can't do it that way. You understand? We can't share this 5 volt reference externally. Is it shared in here? Here and here?
Yeah.
Is it internally shared? Yes. But can we externally share it? No. Not like that. Definitely not. What about...
So if
Go ahead, Dave.
one of the wires internally fail, do both fail externally?
Yes. Yes. And I'll get to that. Good question. What about taking this? Could I do this? Let's see. Get rid of this wire and share that up here. Can I do that? This, remember, for this TPS or whatever to work properly, that needs to be 5 volts right there, right? To get our voltage range correct, this needs to be 5 at the top, because this should be 4, 3, 2, 1, and so on. It needs to be 5 at the top. What's the voltage in here, right there at that leg? Is that 5? It's not 5. Why? What's that going to do? Drops the 5. And what's this do? Drops it even more, depending on resistance. Do you understand that this can't work either? Can't do it. You cannot share, listen carefully, cannot share the reference circuit between thermistors and pressure sensors and potentiometers. You can't share. The thermistor has to be on its own, has to be by itself. What if I have another pressure sensor on here? And there will be. There'll be many. Pressure sensors, potentiometers. Can I do this? Let's extend this computer. Can I take and source from here? In fact, I'll do this like this, just to make a point. Can I make this my TPS down here? Would that work? Can you see that the top of this resistor, this is 5 volts here, right? What would this be right here? If this is tapped into 5, which is, if you look at the diagram here, guys, does this go back to my regulator? Can that regulator handle another load, another branch of current flow? Is that going to cause a drop on that regulator? Technically, yes, but what does a regulator do? Produces more current to maintain it at 5. 12 volts as the source. It has no problem keeping up with this additional parallel branch. So we have current flowing this way. Now we have current flowing this way. That regulator, that's its job. That's what it does. So my point is this. What's my voltage here? It's 5. And my ground, I said we can share grounds, which I just did. So down here would be 0. And so do you see we got 5, 4, 3. Sorry, my pen's acting up. 5, 4, 3. All the way down to 1 on that resistor. And I have a sensing circuit in there for whatever other sensor that is. So you see I can share references and grounds. In particular for this, I can share a reference with pots and pressure sensors, but I can't share a reference with what? Thermistors. Because the reference is the signal on a thermistor. Are we good on that? All right, now let's think about our Pacifica. Again, I wish I would have filmed it. I'm pissed that I did not. This addresses Dave's question, which he just asked. Could we have, I'm rephrasing this. Could we have a problem with one affect the other? That was kind of
like internally.
Internally and externally. Let's do the external one first, because that's what we dealt with on the Pacifica. Let me get rid of this. Go ahead.
There's 2 grounds, so what if you have a short to ground? Does it affect both?
Let's do your first question first, and then I'll address your second.
Because I don't know if, alright.
Yeah, I drew it as 2 grounds up here, Dave, but you know, really there would be 1 ground that would be shared. I'll address that one next. Let's do the first one. What happened with the Pacifica? I think maybe we'll answer Dave's question. We had a cam sensor, which the cam sensor wiring would have been exactly this right here. Okay? The cam sensor was plugged into the ignition coil. And the ignition coil was plugged into the cam sensor. And what it was doing, essentially, was this. With the cam sensor wiring, we were going into a coil. Trying to think of the wiring of the coil for a second. That would have went through a driver, and it would have went to a battery feed. You know what, I'm not going to try to draw that because without knowing exactly what pin on the ignition coil the cam reference wire was, I can't do it. Let me just say this. We were essentially shorting to ground right there. When that cam sensor was plugged into that ignition coil, we were shorting that circuit to ground. Okay? So what's that do to the regulator if the circuit is shorted to ground? Can you see that that regulator would be producing a whole bunch of current? And if this wasn't protected, it would burn out the regulator, it would fry the computer. That regulator that's in the computer would cook it. They're protected, so essentially what it did is it pulled this all the way to ground, so my reference circuit was 0. Do you guys remember that I had us check some other sensors that were on there at that point? What were we testing? I think map sensor I had you check. Weren't we checking the map? We were seeing weird voltage. We were seeing that oscillation in there. And that was because we were connected to the ignition coil. But what was I thinking about? It's time to go to a different picture instead of drawing this. My 5-volt reference circuit. Let me finish this and I'll let you break and we'll go to shop. This is really what we're on right now. Here's a picture. We did this before. When we did the Pacifica, I pulled this picture up for you. If you short out the Hall effect, this is my cam sensor. If I short this 5-volt wire to ground, can you see that that is attached to this main 5-volt reference that's attached to everything? My switch inputs, my thermistors here, my potentiometer here, pressure sensor here, another potentiometer here, the cam and crank, the vehicle speed sensor, they were all connected. What do we do? Pulls the whole regulator to ground. What does that make it? No start, no spark, no communication. Now in our case, we had separate references. We still were able to communicate, right? On that Pacifica?
Yeah.
Yeah, so there's variables with that, but does that make sense how you can have one short, pull the entire circuit to ground? All right, what about, so that should answer your question.
Yeah,
Externally, if we're shorted here, yes. Could we have something internal to the computer short to ground? Of course, we don't see that. There would be no way to know if that was the fault or if the regulator was just dead in that case. And there's, times where you can have a faulty computer and have no reference circuits. We'll talk more about this later. We would start checking computer powers and grounds if that was the case first. Back to Dave's question. What about the thermistor? This is this leg. Could we have, I like my other picture. Could we have a short in the thermistor circuit that takes the regulator out? Could we have a short in this circuit here that takes the regulator out? Answer is what? Yes. So a short here would affect the signal up here. Can you see that? All right. What about our short here?
No.
Nope. See, that'll stay there because what's that going to do? Causes voltage drop. This will drop to 0. This line will be 0. It'll kill this signal circuit on this thermistor, but you understand it'll stay at 5 on this side? Because of this resistor and how the circuit's designed. Guys, on thermistors, that circuit's designed to be pulled to ground. It's intended to do that. It just does it slowly over time instead of a switch input doing it immediately. So, let's say this, and then I'll let you break. A short here will affect the signal here. but a short here will not affect the signal here. Another way I could state that, and I have in section 9 that we were just looking at, is a shorted, here let's look at it, a shorted pot pressure sensor Hall effect may pull down the entire reference, but a shorted thermistor will not. Another way we could state that, a shorted TPS will affect an ECT, but a shorted ECT will not affect the TPS. Cool?
Yeah.
You had one more on grounds before I let you go to...
Yeah, but on.
Anything with the ground? You see in my generic picture that all of my grounds, I've shared them. The TPS, the IAT, the ECT, the switch input, the map sensor, the VAF, and I labeled it signal return. Look where it goes. Goes to the computer, goes to ground. Get used to that term. That's another name for a sensor ground, is a signal return. You see I shared them all in this diagram because we can do that. Cool? So in what, half an hour, we've really dissected a majority of the inputs on a system, on an engine management system and how they work. And guys, this isn't just engine management. This is body controls and ABS and transmission controls and you name it. Climate control, this is what they're doing. It's all the same. It goes so far as this is your PlayStation controller. This is your furnace at home, the high efficiency furnaces that have a DC board that controls the furnace. They have flame rollout sensors and thermistors that work and are designed exactly like this. And with this kind of knowledge, you can test all of this stuff. Know how it works, know how it's designed, know its variables, makes for easy troubleshooting. All right, so tomorrow when we start back into this, we really covered section 9 today and a good bit of the wiring stuff. Tomorrow we'll start in thermistors and I'll give you the description, operation, how it works. There's some other variables with that. You need to know, what its purpose is, how the computer uses it. Why is that important? Think about our car we did yesterday with the bad O2. How did I know so quickly that was a faulty O2? Symptoms told me that. Such as open loop, we don't use the O2. Hey, that car ran good in open loop. Things like that. So same thing with thermistors. Where's the computer use the ECT? What kind of symptoms can I have? What will guide me to that? We have a lot of stuff to cover. But electrically speaking, I mean, this is pretty much it. We can plug in all the variables from there, but this was a good intro. So go ahead and take a break and we'll go to shop.